Okay, good afternoon, everyone. Today we have a guest from Texas A&M University, Professor Patricia Klein. Professor Klein was an assistant professor at the University of Minnesota under the mentorship of Christine Berkish. Before that, she was a postdoc at the University of Kentucky under mentorship of Uwe Nagel, and before that, she completed her graduate studies at the University of Michigan under supervision of Mel Hochster. Yeah, you might actually meet Professor Klein soon. In fall, she will be at the Institute for Advanced Studies for their program on algebraic and geometric combinatorics. And in spring 2025, she will be close by here at Fields Institute in Toronto for the thematic program on commutative algebra and applications. But today we have a pleasure to have Professor Klein here giving a talk.
Today I want to start from some old questions, then move quickly to some new ones, starting with what is enumerative geometry. And then we'll talk about some newer approaches and some combinatorial models that we use to study these questions. So all the way back in the 3rd century BCE, Apollonius of Perga was interested in orbits of planets and in conic sections to study these. And so he asked a lot of questions about conic sections and about how they can interact with each other. And so one of his questions was, given 3 circles in the plane, how many other circles are tangent to those? And we're mathematicians, so maybe we first gravitate towards the degenerate cases. And so, we can picture, all 3 are the same circle, and then there are infinitely many answers. Or maybe I have 3 concentric circles, and then nothing works out. And if we ease into it, maybe we find that there is sort of a typical answer, that if I don't have any of these degenerate coincidences, I have 3 circles sort of scattered about, different sizes, then I want to be either internally or externally tangent to each of them. And in general, I can achieve those goals. So for example, here I am being externally tangent to all of them. Here I am being internally tangent to all of them. And we have these 2 to the 3 choices. Von Neumann gave a nice argument many years later, saying that, well, the center of the tangent circle has to lie on 2 hyperbolas, one each, pick 2 pairs of these circles, and that will trace something out. So you can solve this by taking intersections of these auxiliary geometric objects. But this is a nice, very concrete question coming from, celestial bodies and then down to earth for us. And it's the type of thing that we would certainly think of as geometric. There are circles. And enumerative, I want to count something, and the answer is finite. Here's a more modern question. Suppose that I have 4 long sticks, and I throw them in the air, and then they freeze there. How many other sticks can intersect all 4 of those? Having seen this problem 100 times, my intuition is terrible. I feel like the answer should be none. How do I hit all of those? A line in 3 space, it's basically going nowhere. And so rather than, using my intuition, we can use this nice picture drawn up by my colleague Frank Satile. And here's a better way to think about this problem. If I have 3 skew lines, so not parallel to each other, don't intersect, L1, L2, L3, these determine a hyperboloid, provided they're not all parallel to another plane, which happens almost never. So the typical situation is I take 3 of these sticks, and I sweep out this hyperboloid. I don't just get the hyperboloid, I actually get it with a ruling. So these 3 lines, they're all entirely on this yellow surface, and there's this, I can fill the entire hyperboloid going just sort of in a, continuing on around in this way. And I get those 3 back. The hyperboloid has a double ruling. ruling. So going in the other direction, if I take a line like this M2 here, it necessarily hits each of the 3 lines that cut out my hyperboloid exactly once. So here it is intersecting blue, red, and green. So if I take 3 lines in 4 space, I can cut out this hyperboloid, I can just pick any point on the hyperboloid and take the line that goes through it on the secondary ruling, and I get a line that intersects my 3 given lines. Okay, so that answers infinitely many, and it's not what we were looking for. Instead, what we want to do is we want to take this 4th line, L4, and we're just going to pierce the hyperboloid with it. And when we pierce the hyperboloid with it, we're getting 2 points on the hyperboloid, and they're not on the same line. So this gives me 2 other elements of the secondary ruling, which means that I'm getting 2 other lines that intersect my 4 given lines. So again, by constructing the secondary geometric object, we can do this really nice bookkeeping, and we get this precise, concrete answer. So the answer is 2, and there it is.
Sorry, I have a question.
Yeah.
What exactly do you mean by ruling and secondary ruling?
Oh, so a ruling is just a bunch of lines that don't intersect each other and that fill the space and go all the way around. And so a hyperboloid has 2 of them, and one of them is drawn out here. This is the ruling that's coming from L1, L2, L3. And then there's, oh, sorry, this is the one that's the M's, and the one that's coming from L1, L2, L3 is sort of suppressed. So if you pick, for example, a cylinder, and then just pick, a line that's straight on it, and then just move that line all the way around, that's a ruling of the cylinder. Good question. Other questions? Okay, so enumerative geometry, what have we found so far? We like geometric objects. We like it when we can count stuff. We like being able to use other geometric objects to help us with that count. And we really do much better when these objects are cut out by polynomials. So you could very reasonably ask for intersections of exponentials and sine functions, and I don't think that's intrinsically uninteresting. I just think I don't know how to do it. And so the setting that we'll be in will be using shapes like circles or like paraboloids that are cut out by polynomial equations. And that's the setting of algebraic geometry. In fact, a set of points that that causes some set of polynomials to simultaneously vanish. This makes up an algebraic variety. So a circle is an algebraic variety, a hyperboloid is an algebraic variety, and so on. So these are what we'll be able to study. Other things that we noticed are we have these sort of degenerate examples, and we don't really want those. Sometimes we might be interested in classifying all possible solutions, but much more often we'll be asking, what's an answer that's robust up to small perturbations? So if I'm allowed to move stuff around a little bit, what's sort of the typical answer? And the typical answer happens on a dense open subset. So the typical answer is really typical in a sense that can be made precise. Making this precise, saying which wiggling are we allowed, what counts as a typical answer, this all happened after Schubert did a bunch of the wiggling. So he had these degeneration, sliding things around arguments, and then Hilbert's 15th problem was to put that on a rigorous foundation so it didn't fall apart like some algebraic geometry famously had somewhat recently at that time. So why do we do it? Jonathan Haunstein gave this great talk where he talked, which is recorded and I recommend it, talked about this 4-ball coupler curves, which are also on this shirt. And what they are is you have something like the top of a heavy door and it moves around, and this scrapes out a line, it scrapes out a curve. And it turns out that when you're doing robotics, those points of intersection are the hard things. And so if you can do algebraic geometry and find these intersections of curves and count them and understand them, then you can make really good robots that pick up batteries of all sizes, and it's very exciting. So one application is robotics. Another application is spectral theory, which is a linear algebra thing, and I don't know anything about it. Another application, which I also know nothing about, is computer vision. So how this might work is you have a camera, and the stuff that you might see lives on some algebraic variety. You have another perspective, it lives on some algebraic variety. You want to intersect those to plausibly see, like, what could the 3D image look like. And the final motivation I'll talk about today is that counting is fun. And this is the one I'm most qualified to comment on. So I really like it when we take algebraic varieties and we intersect them, and there are finitely many points of intersection, and we count them in a reasonable way. And that will be what we're doing for the rest of the day, because of joy. So the setting we'll be in is the Grassmannian. So as a set, the Grassmannian is the k-dimensional subspaces of Cn. Everything will be over C today. It mostly doesn't have to be, but it will be for now. These are great as manifold, compact-oriented. They're also projective varieties. So these are algebraic varieties that they're, stuff is nice when it's closed and compact, and this is a setting we can do that in. So for example, if you've seen projective space, this is the one-dimensional subspaces of C to the n plus 1. And if you haven't seen projective space before, let's think about projective P2. So P2 is the set of one-dimensional subspaces of C2. So this is the set of lines through the origin in a plane. Almost all of these lines you can describe by their slope. And so you get almost everything by a copy of C. There's one that you miss, the vertical axis. Also, almost all of the lines through the origin you can describe by the reciprocal of the slope. The only one that you miss is the horizontal axis. And so P1 is covered by these two copies of C, where the intersection is really, really big. It's as far as being from disjoint as possible. You're just missing one line from each of them. So if you've never seen projective space before, let P2 covered by two copies of C, P1 covered by two copies of C be your picture. An element of the Grassmannian can be described by the row space of a matrix. So if we want a three-dimensional subspace of C7, what we want to do is take the row space of an invertible 3x7 matrix. Not all pairs of distinct matrices will give me different subsets. For example, if I scale this bottom row by 2, I'm getting the same row space. But I might as well put it in reduced row echelon form, and then my choice is unique. There we go. So here I am, where I have this identity matrix living inside of it, and then I just have some other stuff. And I have an identity matrix. These have to be zeros. To the left of my ones, I have to have zeros. And these can be 0 or non-zero, whatever you want. They, for example, don't all have to be positive integers less than 10, but they could be. And so this is cutting out an element of GR37, and it's a good choice of representative for it. From the location of the identity matrix, we can read off a partition. And the way we're going to read off the partition is a little bit weird. We're going to say, start from the column of the last column of my identity matrix, subtract 3, and the 3 is coming from my k, from my dimension of my subspace. From the next column index, subtract 2. From this leftmost column index, subtract 1. And because we know we have an identity matrix living somewhere in there, this is getting us now from our representative of an element of the Grassmannian in reduced row echelon form to a partition. We can use these partitions to partition the Grassmannian. So every element of the Grassmannian is represented by exactly one matrix in reduced row echelon form. That matrix is associated to a partition. This is telling me that the Grassmannian is a disjoint union of these subsets indexed by the partitions. We can take a closure of each of these sets. And the closure, if you like the Zariski topology, take it there. If you don't, we're over C, take it in Euclidean space. And this is called a Schubert variety. So let me think a little bit about how this closure happens. So one thing we know, for example, if we're indexed by this particular partition 3, 1, 1, is that our last one has to come here. And so we're zeros to the left, and we're whatever we want over here, 0 or non-zero. And so an element of the Grassmannian, indexed by this partition, 311, has to contain a line that's in the span of E6, E7. Coming from lambda itself, we're missing one. We're missing one line, and it's the one whose slope would be given by 0, 1. Everything else we get. And so if I'm in the plane, and I have all but one of the lines, that shouldn't feel closed to us. We should be able to just sweep the slope of that line over until it doesn't have one, and we're getting our final line, which is the vertical one. And so when we take this Zariski closure, or this Euclidean closure in this case, what we're doing is we're saying, if I say that an element of the Grassmannian associated with this partition has to live inside of the span of these standard basis vectors, we're now just going to allow everything that lives inside of that span. So going from u lambda to scripty x lambda, the difference is whether or not we have the line that's all zeros and a 1 there. So that's what's happening when we take closure. And so on throughout the line. Okay, so those are Schubert varieties in the Grassmannian. What we're going to do is we're going to intersect them until we have finitely many points of intersection, and then we're going to count them in an attractive manner. The famous theorem of Kleiman says that if I take an intersection of Schubert varieties, and it looks like I've intersected with enough stuff to get down to something zero-dimensional, then in fact I have, provided I'm allowed to shift these around. So just like when we had those 3 circles, we didn't want to be asking a question about 3 of the same circles. We wanted to bump them off of each other. If I want to ask about, for example, 2 lines in the plane, I don't want to be allowed to ask about 2 of the same line. I want to say I have to move it a little bit. And so that's what these elements of GLN are doing. So they're a change of basis on my matrix, or a change of flag if you've seen that language, or if you haven't seen either of those, then this picture is right, where you're taking possibly 2 of the same variety and you're sliding them past each other. So when we are intersecting our Schubert varieties, and we hope to have finitely many points of intersection, for most choices of bumping around the varieties, we do. And then our goal is to count them. And an amazing fact is that we can count them using symmetric function theory. So I want to ask you to think about this mu complement as being sort of a dummy variable for us. So we're just going to intersect with the entire space. And so that doesn't do anything to the intersection, and it will be some bookkeeping for us. It'll tell us where to look for a coefficient. So Schur functions have the property that they're an additive basis for the ring of symmetric functions. And in fact, if I multiply any symmetric functions I like, I can then express them as a non-negative sum of other Schurs. I haven't defined Schurs for you. I will later within the context of Schubert polynomials. So the upshot for now is that we want to compute this geometric intersection. We want to count some points. We can do that in a totally algebraic way. And the algebraic way is we multiply a bunch of polynomials, if we want, and then we express them as a sum of other polynomials of the same type, and we read off one particular coefficient. So here's what that looks like in a particular example. So let's be in the Grassmannian GR24. So 2-dimensional subspaces of C4. This Schubert variety corresponding to the partition 2-1 is the set of planes through the origin in C4 containing a particular given line and contained in a particular 3-dimensional subspace of C4. That line and that 3-dimensional subspace are, maybe I can actually point with this. This one, are determined by G1. So our choice of element of the general linear group is telling us which line, which 3-dimensional subspace. But for any of those, it has this property where it's defined by containing a particular line contained in a particular copy of 3 space. And this is information that we can read off from the matrix like we did with that bottom row before. The Grassmannian, the element of the Grassmannian determined by the partition 1, 0, consists of planes through the origin in C4, plane coming from the 2, C4 coming from the 4, intersecting a given plane in at least a line. If we intersect those two things, the codimension is right, and we can tell that the codimension is right because 2 plus 1 is 4, and 4 is the dimension of this Grassmannian up there. So we can find this, we decided, through this Schur function computation down here. So we're multiplying the Schur function coming from the partition 2, 1, and the Schur function coming from the partition 1. And it turns out that it's this sum of other Schur functions. We read off the coefficient of S22. The reason why we do that is because we have this dummy intersection with the entire space, and the partition that's coming out of taking this dummy intersection is the largest partition we're allowed to have. And the largest partition we're allowed to have is n minus k times k. So 4 minus 2 times 2. So the reason we're looking for the coefficient of 2, 2, that's because of the particular Grassmannian that we're living in. So we can do this algebraically, but polynomial multiplication is not fast. And so we're pleased to also have this sort of purely combinatorial rule. This is called the Littlewood-Richardson rule, and here are the rules for it. We take our largest available partition, 2, 2, and we subtract off 1. This 1 is this new there. So we get rid of this box. And then we fill it subject to certain rules. One rule is that I have to have 2 1s and 1 2. So our second partition, mu in this case, is telling us what numbers have to go in those boxes. Once we put the numbers in those boxes, we ask, is this an allowable filling? Allowable filling means two things. One is that it has to be semi-standard. And the other thing that it means is that if I perform this algorithm called rectification, meaning if I slide these boxes around to get rid of this missing corner in a particular algorithmic way, I have to get a tableau that has all 1s in the first row, all 2s in the second row, all 3s in the third row, and so on. So if you've seen Tableau combinatorics before, you've probably seen rectification, and so that maybe means something. If you haven't, then the upshot of this is that we want to answer a geometric question, which is how many points of intersection are here. We can do this algebraically in a hard way. Polynomial multiplication is hard. We can also do it in a purely combinatorial way, following rules about what shape of tableau can I have and what fillings are allowed. So those are our 3 closely related pieces of data. Okay. Let's go again to, if I choose now 4 copies of this, translated differently, then I have 4 planes in C4. And I insist that these 4 planes, I'm asking how many other planes meet all of these 4 planes in at least a line. So I have 4 things, and I'm asking for other of the same thing that meet that thing in 1 dimension smaller. And this feels like something we did earlier, and indeed it is. And precisely in what way is this, again, the 4 lines in 3 space question? It's because we can take this quotient from C4 to P3, and then planes become lines and lines become points. So this question that we wanted of 4 lines in 3 space, we can, thinking projectively, bump this up to a question about the Grassmannian, and then we can answer this question about the Grassmannian using either symmetric function theory or Tableau combinatorics. And so other similar questions, maybe we don't have a nice hyperboloid that we can draw, they can also be answered by bumping up to the Grassmannian in this systematic way. So precisely what is the Littlewood-Richardson rule? It's saying if I have 3 general elements of GLN and I have three partitions that live in this largest allowable box, n minus k times k, then the number of points of intersection is expected to be the coefficient of this s omega in the expansion of s mu times s nu, and again, these are Schur functions. One thing that you noticed was that there wasn't a distinguished, I had mu and nu playing different roles in the last example, and maybe that looked odd because the intersection was symmetric. And so it's a theorem that actually you have the same number of Littlewood-Richardson tableau viewing one of these as a shape and the other one as the content or vice versa. So this number is called a Littlewood-Richardson number, or in a more general context, a Schubert structure constant. This concludes the Grassmannian part of the story. What questions are there about Schubert varieties in the Grassmannian before we move on? So in summary, geometric object, counting number of points of intersection, do this through algebra or do this through tableau combinatorics. We'd like to do this more generally. And so, not just the Grassmannian. The Grassmannian was saying, take maybe the origin living inside of one subspace of a particular dimension, living inside of all of Cn. But now we're going to just saturate this chain. So now I want to record the information of the origin living inside of a one-dimensional subspace, living inside of a two-dimensional subspace, living inside of a three-dimensional subspace, and so on. I'm remembering all steps of the process. So this is called a flag, because we have a point living inside of a line, living inside of a plane. This is how it gets this name. So this set of complete flags is acted on transitively by the general linear group. The stabilizer of the flag determined by the identity matrix, we're getting our flag same way. So span of bottom row, span of bottom two rows, span of bottom 3 rows, and so on. The stabilizer is the upper triangular matrices. So using the orbit stabilizer theorem, we can identify the set of flags with this quotient GLN mod U. This quotient is a quotient as groups. It's also a quotient of topological spaces. So this bijection that we get through the orbit stabilizer theorem is endowing the set of flags with a variety structure. So that's how we're calling it the complete flag variety.
Sorry,
yeah.
By groups. Is U normal?
Oh, I hope so. Nope.
Is there some
I want to take back everything that I've said and just say that the set, yeah, and maybe there's nothing. The relevant fact is that we're getting variety, so it's a quotient of topological spaces, and I should not have said anything at all about groups. Thank you.
There's not like some group structure that you can put on this.
I've already done so poorly. I want to not, but I think no. Okay, so we have, just like in the previous setting, we have these matrices. It is not the case that two different matrices necessarily give me two different flags. There's this equivalence class of them. And so, but we might as well just take one. We can write this matrix and we can give an LU decomposition. And most of the time, we don't have to do any permuting in the middle, but occasionally we do. And when we do, there's a unique choice of permutation that we put in the middle so that we can write it in this way. So GLN is expressed as the disjoint union of lower triangular matrices, permutation matrix, upper triangular matrices. This is called Bruja decomposition. So this is what is going to give us our Schubert structure in the complete flag variety. It's pushing down this decomposition through the quotient map of topological spaces, going from GLN to the complete flag variety. We take closure again, and we get a Schubert variety. So now we are in the complete flag variety, and we have these varieties that are indexed by permutations, and play sort of well with combinatorics. So again, we might want to ask, if I intersect them and I get finitely many points of intersection, how do I count those intersections? So so the integral cohomology ring, what does this mean? This is just a ring that's recording if I intersect enough of these varieties to get down to finitely many points of intersection, how many are there? That is what this ring is. And so Borel showed that there's this isomorphism from this ring that's about the intersections to this nice ring that is over Z, generated by n variables, and we quotient by the ideal generated by the non-constant elementary symmetric polynomials. It turns out that this quotient ring has really, really good representatives. These representatives are called Schubert functions, Schubert polynomials. So Schubert polynomials are generalizations of Schur polynomials, which we'll describe how in a second. But these have the property that if I multiply two Schur polynomials, I can express them as a finite sum of other Schur polynomials. So the Schuberts form an additive basis of this ring. And so the kind of surprising fact is that this quotient is so well behaved, that there's no cleanup in the quotient. There's no secret plus I that I'm suppressing here. This is on the nose how we're expanding this. And so these Schubert structure constants here that are by definition of the cohomology ring telling me how many points of intersection are there for the Schubert varieties associated to U, V, and W. They're also just coming from polynomial multiplication. So here is a definition of them. This was the first definition given by Lescaut and Schutz and Berger. It's a very, very explicit one that I work with never. So you're going to start with this monomial that's associated to the longest word. And for each simple transposition, you have this divided difference operator. So you take your polynomial, you plug in x for x minus 1 and x minus 1 for x, and then you divide by xi minus xi plus 1. This might look like a rational function. That denominator, though, is an optical illusion. This is, again, a polynomial. You land back in this ring. So to each permutation, you can choose whatever reduced word you want. Divided difference operators satisfy the braid relations. You can define a polynomial that's coming from just applying the appropriate divided difference operator determined by your permutation to this sort of starting monomial. So that's a definition of Schubert polynomials. If my permutation has at most one descent, so here's an example of a permutation with at most one descent. It goes 2, 3, 6, 1, 4, 5, 7. So it goes up, 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 down at most once, and then up, up, up again. So if it has at most one descent, then its Schubert polynomial is the Schur polynomial associated to its partition. So how am I associating permutations with at most one descent and partitions? In the following way. Let's think about this matrix that was associated to 3, 1, 1 in our Grassmannian setup. My rule for getting a permutation is that I'm going to take the columns of the identity matrix, 2, 3, 6. I take them in order, so I'm necessarily going up. And then I'm going to take the columns that are not part of the identity matrix. So 1, 4, 5, 7, 1, 4, 5, 7. So this, we can always go through the matrix. The matrix is giving us the partition. The matrix is also giving us the permutation. And so in this way, we are seeing Schuberts as a generalization of Schurs. So what we've seen so far is that we're interested in intersections counting finitely many points. In the Grassmannian, we can do this through algebra, through the Schur functions. We can do it through combinatorics using tableau. Over now in this more general setting of Schubert varieties and the complete flag variety, we have our geometric question, and we can do it through algebra. And so a natural question is, are you going to tell us now how to do that with tableau combinatorics? And indeed, I am not. So that is the major open question of this field, is how close can we get to being like the Grassmannian? How well can we do in giving combinatorial models that replace this algebra, multiply polynomials, and expand? How close can we get to giving a combinatorial rule or set of rules that tells us directly about the intersection theory? And there have been some generalizations, and I'll tell you very briefly about these. So your colleague, Kevin Perdue, and my colleague, Frank Satile, gave these filtered tableau that did the case in a more general flag manifold. Your colleague, Oliver Pechenik, and my collaborator, Anna Wygant, did these P-inverse Grassmannians. So this case is about the same size as Littlewood Richardson, and they do this through rainbow combinatorics, and Oliver, I'm sure, will be happy to tell you more about it. The things without dates are fresh, still going through publication. So Alan Knudsen and Paul Zangerstin have these puzzle rules. So this is for the case of separated descents, meaning that the last descent of my first permutation occurs at or before the first descent of the second permutation. And so the two permutations that are inputs give you input for a puzzle. You solve these puzzles relative to certain rules, and then the puzzles that you get out tell you how to read off the Schuberts that show up in the expansion. And also the separated descent case, by a totally different means done recently by Daoji Huang through bumpless pipe dreams. So bumpless pipe dreams look like this, and they will make up roughly the rest of the talk. So these are the types of rules that we like for addressing Schubert calculus. Things where, at least in small examples, we can write them down, we can move them around. They don't have to be tableau, but sometimes they are. And they're in general sort of have this toy feel. So now let's talk about pipe dream. Actually, maybe before I do this, are there any questions on our goal? Where our, I mean the entire field of Schubert calculus. Are there questions on the goal? Okay. So here was sort of the beginning of pipe dream combinatorics and Schubert calculus. So we really, really want to understand these Schubert structure constants, and a lot of people have worked on it for many decades. It's very hard. And at this point, we maybe want more ways to look at Schubert polynomials. We want more models for Schubert polynomials. We want more approaches. And so what pipe dream combinatorics is doing is it's giving us new ways to look at Schubert polynomials. So that's sort of the sub-goal that we're addressing here. Bergeron and Billy called these RC graphs. And combining their work with Fomin Kirillov, you can use these things called pipe dreams to write down a Schubert polynomial. So here's what a pipe dream is. It's a tiling of this grid subject to certain rules. So you're allowed crossing tiles, you're allowed these bumping tiles, you're allowed these elbow tiles. You always live above this diagonal, and these pipes have to trace out the permutation. Here's how they trace out the permutation. You start here, you follow the pipe, and you ask what column did you get to. So I trace here and I get to column 2. I trace here and I get to column 1. I trace here and I get to column 4. I trace here and I get to column 3. So that tells me 2, 1, 4, 3. So that's that permutation here. And if we did the same with these two pictures, if we traced our pipes in the same way, we would again get 2, 1, 4, 3. And with our rules, we also don't want two pipes to cross once. Sorry, we don't want them to cross more than once. We're getting all of the ways that we can do this. So another way to think about this is through these, what Bergeron and Billy called chutes and ladder moves, where we're going to take this crossing tile and we can slide it along this diagonal. So that's actually, in this case, the only allowable move. But you can always sort of start with the pluses justified and then slide them subject to these rules. So once we write down all of our pipe dreams, how do we write down the Schubert polynomial? Well, we look in each pipe dream and we ask, where do the crossing tiles live? Here, they both live in column 1. So that's giving me an x1 squared. Here we live in column 1 and column 2. That's giving me an x1, x2. Here they live in column 1 and column 3. That's giving me an x1, x3. So by writing down all of the pipe dreams for a permutation, you can then read off the Schubert polynomial. You can also read off what's called the double Schubert polynomial. This is telling you information about the equivariant cohomology. You can also, from these graphs, read off reduced words for the permutation. So they're very flexible and very useful. They also come from geometry. So Fulton introduced matrix Schubert varieties. And these are affine varieties that sort of live over and record information about Schubert varieties. So this is coming from a degeneracy loci story. It's not something sort of as, the story's a little bit involved. But the upshots are that the geometry of these affine varieties and the geometry of Schubert varieties are closely connected. So we said that varieties have defining equations. Algebraic varieties are defined by vanishing of polynomials. The polynomials for 2, 1, 4, 3 are this monomial and this 3 minor. And there is this degeneration technique called Grobner degeneration, and it gets you to a monomial ideal. This monomial ideal is also recording information that we can read off from the pipe dreams. So this 1, 1 is coming from the location of this cross, 1, 1. This 3, 1 is coming from this cross, 3, 1. This 1, 1 is that 1, 1. This 2, 2 is that 2, 2. This 1, 1 is that 1, 1. This 1, 3 is that 1, 3. So by taking this degeneration of the variety, taking its components, and then reading information from the components, we get back the crossing tiles for all of the pipe dreams, and so we get back the Schubert polynomial. And let me show you one quick picture of what Grobner degeneration looks like. So not in that case, but in a smaller one. So here is a perfectly good algebraic variety. It's the vanishing of xy minus z squared. What Grobner degeneration asks us to do is for each polynomial, choose one monomial to represent it in a systematic way. And so when we degenerate this variety, we might say, okay, z is going to be really important. I'm going to assign a really heavy weight to it. And what that is doing is it's squashing the whole variety down to this plane. This is over R. If it were over C, you'd get the whole plane. And so this we want to think about as really two planes hovering over each other right there. So we want to remember the information that this plane is coming to us with multiplicity 2. And so if we're interested in points of intersection, one thing we can do is take points of intersection once we're down to this union of subspaces and then sort of undegenerate and lift them back. And there are people in the numerical side of this world who do that. The other choice we might make is we might say that, okay, this term is going to be really large, and the z squared is going to be really unimportant. And when we do that, we get this union of 2 planes. So we're taking our variety and we're squashing it until it's a union of planes, and maybe we get all different planes, or maybe we get the same plane with some multiplicity. Where we get different planes, this is much easier. Derivatives play better. We can sort of undeform stuff in a more reliable way, and also just the combinatorics is easier. It's going to feel rude in a second, but in some ways better behaved, because we don't have to remember multiplicities. We're just asking which subsets of the axes occur. So our degeneration in this case, our degeneration in this case looks like the degenerating to 2 distinct planes version, where we have we're taking this matrix Schubert variety, we're degenerating it, and we're getting the union of these three copies, well, of sort of a large space. But these three linear spaces. And these, just recording which linear spaces occur, is telling us about these pipe dreams and telling us about the Schubert polynomial. Here are some newer objects. So these are called bumpless pipe dreams. These do not have the bumping tile. Again, we're going to trace out our permutation we're going to start here. We're going to follow this pipe. So we get to the second row. We get to the first row, so that's a 1. We get to the fourth row, so that's a 4. We get to the third row, so that's a 3. And the same with these. So in this case, the set of bumpless pipe dreams is connected by what are called droop moves. And droop moves look like these two things, where this thing, it gets sad and it droops into here. Or the other one gets sad and droops into there. So we can write down all of the bumpless pipe dreams corresponding to 2, 1, 4, 3 just by starting from this bumpless pipe dream and then doing all of the allowable droop moves. This again, it turns out, records the Schubert polynomial. And this time we're going to look at the blank tiles. So this is 1, 1. That's giving me this 1, 1. Oh, sorry. This is in row, no, this is in column 1. This is in column 3. That's giving me 1, 3. This is in column 1. This is in column 1. That's giving me 1 squared. This is in column 1. This is in column 2. That's giving me x1, x2. So our blank tiles in these combinatorics are again recording our Schubert polynomial. So we have these two sort of similarly named, but otherwise kind of different looking combinatorics, both giving us a Schubert polynomial. One of them was connected to geometry. And my theorem with Anna-Wygant is that this degeneration, this formula for the Schubert polynomial is also connected to geometry. So in this, in the Knudsen-Miller setup, what a mistake. In the Knudsen-Miller setup, the distinguished monomial in our polynomial that we chose, well, there's only one choice here, and here we chose the anti-diagonal of the matrix. So we chose the most important monomial from this determinant to be that one. On the bumpless side of the story, we have to choose a diagonal term order. And we won't get a Grosvenor basis unless we zero that out. And so this is telling us that we want to take Z11, Z12, Z21, Z12, Z33 to be the lead term. And that's giving us our 1, 2, 2, 1, 3, 3. And then we read back to the bumpless pipe dreams, 1, 1, 3, 3, 1, 1, 2, 1, 1, 1, 1, 2. So again, the geometry, the degeneration is connecting the combinatorics and the Schubert polynomial. On this side of the story, we have these degenerations that look a little bit worse. They look like the z squared. And so the hard thing is tracking the multiplicities. In the other case, everything was reduced. So now that we have these sort of two sort of ends of the spectrum, one where the anti-diagonals are always best, one where the diagonals are always best, what do we do now? And the answer is that there's a lot of interpolating between them. So there are these hybrid pipe dreams that really go, sometimes you take diagonal, sometimes you take anti-diagonal. There's these closely related things, generic pipe dreams that Knudsen and Justin used to study scheme of commuting n-by-n matrices. Whether or not this is reduced is a big question. Tianyi Yu has many, many different formulas for Schubert polynomials that come from viewing these as two ends of the spectrum. And there are things that, and Daoji Huang and Pasha Piliavsky use these to generalize RSK, and they do some sort of honest Schubert calculus, meaning the conclusion of their paper is, here are more formulas for Schubert structure constants. And the bumpless pipe dreams are things that I still like for, or you know, among many things that I like about pipe dream combinatorics, one of them is that it allows me to study some algebro-geometric invariants of these things called alternating sign matrices. It turns out, you know, if you're on the enumerative side of things, you certainly know that enumerating the alternating sign matrices was a big deal. And it turns out that they just happen to be the natural indexing object for arbitrary intersections of matrix Schubert varieties. So when we do our intersection theory, we're just sort of forced to encounter these. And pipe dream combinatorics gives us some more leverage on them. So with that, I will end, and here's our hyperboloid again.
Thank you for the talk. Now it's questions period. If there are any questions, please wait until I pass you the mic so we get it recorded. Are there any questions?
What's the most exciting open question?
Oh, what are the Schubert structure constants? That's, yeah, that, I mean, that's sort of.
Is there something between what's been done and that?
Yeah, so the, yeah, good question. So Schubert times Schur is maybe the next big deal. And some people think that Schubert times Schur is not meaningfully easier than Schubert times Schubert. And so, but this is a thing where occasionally people become very excited and they think that they've done Schubert times Schur and it is a big deal. And then they realize that they have not done Schubert times Schur. So that's the, if there's a stepping stone, that's it, that's the big one.
Could you give us an idea as to why pipe dreams are called pipe dreams?
Oh, if only I'd prepared. So Alan Knutson really likes this video game from the 90s. And in this video game, there are people playing on these pipes. I'm not a video game person. But they look like the combinatorial object. So Alan likes video games is the answer for why are pipe dreams called pipe dreams. And occasionally people will show a slide from that video game. By people, I mostly mean Lily, who visited here last summer and possibly showed that picture then. But that is the complete answer. Alan likes video games. These are, the bumpless pipe dreams are called bumpless pipe dreams because Thomas Lamb really thinks that's an excellent name. Because there is no bumping tile. That is one of the features of bumpless pipe dreams. I have a lot of mathematical respect for Thomas Lamb.
Maybe the last question, if there is any. If
We
not,
can cut that out of the recording.
let us thank the speaker.